Hello. So in the previous sessions we could prove the Liouville's theorem mathematically. Now we will have a discussion on the physical significance of this particular theorem. So let's revisit the mathematical form of Liouville's theorem to begin with. So it states that the total time derivative of the density function d rho by dt is equal to 0. So this is the most compact form of Liouville's theorem, where rho is the density function. Okay, where rho is the density function q, p and t. Density function representing the system or corresponding to the corresponding region of the phase space of the system. Corresponding to every system we can define a density function. Now we have shown during our derivation that d rho by dt can be re-expressed as, that is, d rho by dt is equal to by using Euler expansion we have shown that is equal to the sum of two other terms, that is the Poisson bracket of rho with h plus the partial derivative of rho with time. So we can say that this becomes a much broader way of representing the Liouville's theorem. So let me call for the time being this one as equation number 1. Now let's discuss what actually is the significance of each of these two terms on the right side of d rho by dt. Rho in general is a function of q, p as well as t. I have been telling about this one earlier also, where this q and p are the spatial coordinates of the phase space. So these two are, always remember, these are the spatial coordinates of the phase space, and t denotes the time dependence of the density function, okay, even at the same point. So we can say that t functionality shows the temporal dependence of rho. So you can view this dependence in two different ways. One thing is that you can think about the variation in rho at a particular value of q and p. What is meaning particular value of q and p? Means we are fixing the observation point in phase space, and you go on observing what will happen to the phase space density at that particular locality as time varies. Okay, so we can see that this d rho by dt involves both the variation of rho with respect to time as well as the variation of rho from point to point in phase space. Okay, so here let me just put up it like this. In equation number 1, dou rho by dou t. What is this dou rho by dou t? Dou rho by dou t is the is due to or it represents the explicit dependence, is due to explicit dependence, means direct dependence, explicit dependence of rho on time. So dou rho by dou t represents the temporal variation of the density function with respect to time, or it denotes the explicit dependence. Explicit means how it directly depends. Okay, now, and what is the other factor? The other term, rho h. Rho h is with respect to qp, the definition of Poisson bracket, okay, which involves partial derivative with respect to q and partial derivative with respect to p, which denotes how these quantities vary with respect to QP, the different coordinates of the phase space. Okay, so we can say that rho h is due to, it is due to the implicit time dependence. This is due to the implicit time dependence. Implicit time dependence. So I'm defining the time dependence itself as what? Explicit and what? Implicit. Implicit time dependence, because you can see that it is d rho by dt on the left side, so it's a total derivative. So total derivative due to one term is there due to explicit dependence, and the other term is due to what? The implicit dependence. Now let's see what's the meaning. Okay, suppose, so let's take a case. Suppose if, you can say, if rho does not have any explicit time dependence. Okay, if rho, let's think that rho is not having any explicit time dependence, which means that mathematically if d rho by dt is equal to 0 for a given system, if d rho by dt equal to 0, you know that what is meant by d rho by dt equal to 0? So it means that the system under consideration is already in a state of equilibrium. So you know from our previous discussion of stationary ensemble, t equal to 0 for any ensemble, then the system will be in a state of equilibrium. System is in equilibrium, and we call the corresponding ensemble as stationary ensemble. Such an ensemble is what is known as what? The stationary ensemble. Or we have seen that a stationary ensemble corresponds to a system in equilibrium. And you know that in general, every system need not be in a state of equilibrium. That's a very special case of a system. A system may be in equilibrium, may not be in equilibrium. But we take a special case where the system is already in equilibrium. So if that is the case, then what does equation number 1 indicate? Equation number 1 indicates that, therefore, equation number 1 says that, you know, by Liouville's theorem, d rho by dt is equal to 0 always. That is equal to 0 always. Okay, but dou rho by dou t may be 0, may not be 0, depending on whether or not the given system under consideration is what? In equilibrium or not. So I write equation number 1 again as, I'm just putting the 0 on the other side, so that you can understand that d rho by dt is always 0 for any given ensemble. So that is equal to simply rho h. That is equal to simply rho h, the Poisson bracket of rho with h, because already dou rho by dou t equal to, assumed to be equal to 0. Now what does it mean? It means that the Poisson bracket of rho with h should be equal to 0. And I hope you remember from our classical mechanics discussions, we have seen an important property of Poisson bracket. What is that important property of Poisson bracket? It was saying that if the Poisson bracket of any variable is not, the Poisson bracket of any function or any observable u with the Hamiltonian of the given system, if that is equal to 0, then what is the meaning? It means that that particular observable should be a constant of motion. So that was a very important theorem result in our Poisson bracket theory. Okay, so what is the implication of that theorem in equation number 2? So it means that for this case, it denotes that rho is not equal to a constant. So rho is perfectly equal to a constant. So that is rho equal to a constant. So which means that the rho becomes, is not, that is rho is independent of, that is for a stationary ensemble, rho is independent of QP as well. And that's a very interesting result. Okay, how did we begin with? We assumed that the system is in equilibrium. Therefore, dou rho by dou t is equal to 0. There is no explicit dependence of the phase space density on time, which demands that the Poisson bracket of rho with h of the system must also be equal to 0. And from the concept, we know that it demands the rho should be a constant. Hence, rho is independent of QP as well, or rho is a constant. Rho is a constant everywhere, right? Alternatively, okay, or in other words, we can say that if dou rho by dou t equal to 0, equation 1 demands that Poisson bracket rho h equal to 0 for d rho by dt to be equal to 0, or rho equal to a constant independent of q and p, the phase space coordinates. Okay, now what is so special about all these discussions? Sorry, what is so special about all these discussions? Actually, rho equal to a constant. You see, this is a very important result. Let me just underline result here for you. Rho equal to a constant. Rho equal to a constant for a stationary ensemble. It points that, what does it mean, rho equal to a constant everywhere? See, okay, let me just draw this one. See, rho equal to a constant means what? In the accessible region of the phase space, the representative points are distributed uniformly. That's the meaning. Is not correct? Rho equal to constant means what? It is not depending on QP. So whether you take a point around here, you take a region around this point, you take a region around this point, you take any region around this point, in the accessible region of the phase space, the rho is obtained to be a constant. It means that the representative points, because rho is the number of representative points per unit volume of the phase space. So when density equal to a constant means the these representative points are uniformly distributed, right? So that is, we can say that what is this representative points denoting? Each representative point is known as an element of the ensemble, and corresponding to each representative point there exists a unique microstate of the system as per our concept. So what is the conclusion of rho equal to a constant? Rho equal to a constant, it denotes that the elements of the ensemble are uniformly distributed over all possible microstates. The elements of the ensemble are, so that is my conclusion. Okay, rho equal to constant. See, rho equal to constant denotes that the elements, so this is the conclusion, the elements of the ensemble, you know what is this each element of the ensemble? That is the representative points, or we can say that the microstates, right? Each representative point is denoting a microstate. Elements of the ensemble are uniformly distributed, elements of the ensemble are uniformly distributed over all possible microstates, and I think that this statement is quite familiar to you. Okay, or is not? Why? Or any member of the ensemble is equally likely to be in any one of the possible microstates. Is not the other way of putting the same sentence? Or any member of the ensemble, okay, any member of the ensemble is equally likely to be in any one of the possible microstates. What is that thing? It is nothing but the statement of equal a priori probability. So that is the physical significance of Liouville's theorem, because you remember that we began our discussion of stat mechanics with telling that there are some fundamental postulates, there are some fundamental hypotheses which doesn't have a mathematical proof of its own, right? So one such postulate was the statement of equal a priori probability. Okay, in the absence of any other information, we are tempted to believe that all microstates are equally probable. Okay, and the second one was the ergodic hypothesis, which says that the long time average of any physical quantity is equal to the average for appropriate statistical ensemble, or ensemble average is equal to time average. Both of these statements are not having a direct proof of its own, but many other results will alternatively prove that these statements or these hypotheses are valid. And we can see that the Liouville's theorem, which was developed independently, is finally confirming or finally testing our statement of equal a priori probability to be a valid one. And hence we can say that this is one of the success of Liouville's theorem, or this can be understood as the physical significance of Liouville's theorem. So let me conclude this session saying that okay, the Liouville's theorem actually justifies the statement of equal a priori probability. Okay, so we will be using the Liouville's theorem in the discussion of the flow of representative points in phase space. And okay, once again, just before we conclude the session, recall what is Liouville's theorem. The theorem states that the local density of representative points as observed by an observer moving with a representative point remains constant in time, or put in other words, a swarm of representative points moves in the phase space in the same manner as an incompressible fluid moves in the physical space. Okay, think on it more. Thank you.